Hi everybody, it's Mrs. Foskett, and this is my first video that I've made for you guys to watch at home. And this video will be the first half of chapter 2, and this video itself will be a bit of a history review for you since you've had most of this material last year. And then we'll pick up with a second video that finishes up the chapter. So I hope you enjoy. So if we go back and we think about the early history of chemistry, so why is there chemistry? Well, basically it's been since the very beginning of man, there's always been somebody who's trying to explain what's going on. So even as far back as the Greeks, previously we talked about Democritus and Aristotle, and they were just trying to come up with ways to explain the things that they saw going on around them. And then so as science progressed, we got to a stage of the alchemists. So these guys are the ones that I equate to like Gargamel from the Smurfs. You know, they're trying to take lead and turn it into gold. You know, so you can take your Smurfs and turn it into gold and things like that. So a lot of their ideas weren't based on sound science practices because they didn't have a firm grasp on what a good technique was, how to measure things, and they certainly didn't understand what was going on. One thing they did do during that time was learn how to prepare acids. So here when it says mineral acids, what that is really referring to as learning how to prepare things like hydrochloric acid, sulfuric acid, and things like that. So one of the first people to really be considered a chemist was Robert Boyle. And what made him different from everyone else was the fact that he was one of the first people to finally perform quantitative experiments to actually measure things. And so that was a huge step forward. And he was also the first to develop an experimental definition of what an element was. So he basically thought that an element was something that couldn't be broken down any further. So he was really on the right track there. All right, so our early chemistry really gives us three really important fundamental chemical laws that we use still to this day, that they stand true. So the first one is the law of conservation of mass, and we have Lavoisier to thank for that one. And that law basically says that mass is neither created nor destroyed in a chemical reaction. And so the law of conservation of mass is basically, you can thank Mr. Lavoisier for stoichiometry. He studied combustion and he realized that quantitatively what he put into the combustion reaction he also got out at the end, mass-wise. So that's how he came up with that one. All right. Next, we have the law of definite proportion, and this was given to us by Proust. And so what Proust found with this law of definite proportion was that anytime that you have a compound, it always contains the exact same proportion of elements by mass. So what does that mean? That means if you have water, that it will always have 2 H's and 1 O. All right, so if you have carbon dioxide, it will have 1 carbon, 2 oxygens. So by mass, those things are always the same. And so that was important in understanding that every water molecule is the same. Every carbon dioxide molecule is the same. Okay, our third law is called the law of multiple proportions. And this is given to us by Dalton. And so what this tells us is, if you have 2 elements that form a series of compounds, I want you to think of something like, let's think about nitrogen and oxygen. We can have NO as nitrogen monoxide, we can have NO2, we can have nitrogen dioxide, and we could have NO3 nitrogen trioxide. And when you have a series of compounds like that, the ratio of the masses of the second element that combine with 1 gram of the first element can always be reduced to small whole numbers. So what does that mean? That basically means that you can't put sort of half an atom of something together with 1 atom of another. So they always have to be in whole number ratios, and that there can be, in certain cases, multiple ratios between certain elements. Okay, so speaking of Dalton, of course gave us the atomic theory, which has 4 points, and most of them have stood the course over time. It's been over 200 years, and most of these we can still believe fully, and the other ones, if we just tweak them slightly, they still hold true today. So the first part of Dalton's atomic theory is that each element is made of tiny particles called atoms. I think we can all believe that one. The next one is the atoms of a given element are identical, or the atoms of different elements are different in some fundamental way or ways. Now, if you think about this one carefully, this may be where you start to say, well, is every atom of an element completely identical? So if you think back to something like isotopes, you can see how this bit of the atomic theory needs to be tweaked a little bit for what we know in more modern chemistry. All right, the third section is that chemical compounds are formed when atoms of different elements combine with each other. And a given compound always has the same relative numbers and types of chemical atoms. All right, so this part of the theory says that chemical compounds happen when there's a chemical reaction. And I think that we can all still support that. Next, we have that chemical reactions involve reorganization of the atoms or the changes in the way that they're bound together. So we have to remember, though, that a chemical reaction doesn't change the atom itself, but it just changes the way that things are put back together. Okay, so after we had Dalton in presenting his atomic theory, we want to go into some of the early work that helped to characterize what the atom looks like. And even though to us the whole idea of course there's a nucleus, of course there's electrons that move around the nucleus, we have to remember that initially that those things weren't known, and there were some really interesting experiments done that showed these things. Now again, you might remember a lot of this from chemistry last year, again with our timeline projects, but I just wanted to go over a few of the important scientists and highlight some of the works that they did. And one of the most important was J.J. Thomson, and this is the plum pudding guy. Right, so he had that came up with that model after he did his work with cathode ray tubes. All right, so remember that what Thomson did was to use a cathode ray tube, which right here is a picture of a cathode ray tube. So it has metal electrodes on each end. We have a negative anode, and over here is our cathode. And so what he did was hook this up to some sort of electrical current, and it produced a beam through the middle of his cathode ray tube. And so from this, he was able to calculate a mass charge ratio for the electron. And since Thomson knew that the atom was neutrally charged, and since he found these negatively charged particles, he knew that there must be some sort of positive part of an atom, but he wasn't really sure what was going on. So he's the one who gave us this plum pudding idea. So we would have this sort of positively charged goo with these negative electrons sort of just sort of thrown in there. All right, so the next important guy that I want to talk about is Robert Millikan. And Robert Millikan was important because he figured out the charge on a single electron. And the experiment that he did was the famous oil drop experiment. So I have a quick video here to show you.
In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19th coulombs. He took this to be the charge on a single electron.
All right, so Millikan's work was important in determining the charge of the electron and in fact, proving that the electron was negatively charged. So, all right, so we know now that we have a negatively charged electron, but we still didn't really know how the electron came together with some sort of positive charge to give us the atom. So, also near this time was the work of Henry Becquerel, and I'm presenting Becquerel to you now, but you should also associate him with the Curies, Marie Curie and Pierre Curie. The Curies were students in Becquerel's lab, and they all won the Nobel Prize together for the identification of radioactivity. So Becquerel was important for leading that discovery. And so what he did was look at the emission of radiation by uranium. And through his work led to the discovery of the 3 types of radioactive emission, including gamma rays, which are basically just a high energy you can think of it as a high energy light. If you think back to what our electromagnetic spectrum, gamma rays are going to be on the high energy electromagnetic spectrum on the far end. Then we have beta particles. Beta particles are just high speed electrons. And then finally we have alpha particles, and he determined that alpha particles are a particle with a +2 charge. And as it turns out, that these alpha particles turned out to be helium nuclei. Speaking of nuclei, our next important researcher I want to talk about is Ernest Rutherford. Now, Rutherford is important because he's important for the discovery of the nucleus. And he did that through doing his gold foil experiment. And what he found was that an atom has this really dense, super dense positive core. And he called that the nucleus. And then the electrons somehow travel around the nucleus at a large distance relative to the nucleus. So it's really hard for us to get our brain around what that scale is. But if you think of something like a BB, like a BB from a BB gun, if that was the nucleus, then the entire atom would be as large as a sports stadium. Or you just have to remember that nucleus is really tiny and dense. and those electrons are diffuse, and the area of the electron cloud is huge in comparison. Okay, so just to review that we now know that each atom contains electrons, right? They're found outside the nucleus, they're negatively charged. And we basically say that the mass of an electron is negligible. Next we have protons. They're found in the nucleus, they're positively charged, and the positive charge is equal to the electron's negative charge. So if we say that an electron is -1, then a proton's +1. And then finally we have neutrons, which are also found in the nucleus. They have no charge, and they have virtually the same mass as the proton. And we'll talk more about neutrons when we get into isotopes, which are coming up soon. All right, so again, that we have to remember that the nucleus is really small compared to the whole atom. It's extremely dense, and the nucleus itself contains almost the entire mass of the atom. Of course, the electron has to have some mass, but since it's so small, it's again, the electron itself, that mass is negligible when you consider the mass of the nucleus itself. So if you want to try to envision what an atom looks like in 3 dimensions, it's kind of hard to do because, we think all the time we think in 3 dimensions, but we see things in a 2-dimensional world. So if you can try to envision what this might look like if we had a nucleus with a diameter of 10 to the negative 13 centimeters, but then scale-wise, then the entire electron cloud is going to be like 2 times 10 to the negative 8. So again, the electron cloud is much, much larger than the nucleus itself.